Hi everyone, welcome to another Monty Heart video today from the lecture series. It's a great honor to have today Dr. William Cohn, who will be speaking about the past, present, and future about the total artificial heart. So Dr. William Cohn is the Chief Medical Officer of Vivacor and the Executive Director of the Center of Device Innovation at the Texas Medical Center. He's also a tenured professor of surgery at Baylor College of Medicine and an adjunct professor of bioengineering at Rice University and the University of Houston. Prior to joining Vivacor, he served as vice president at the Johnson & Johnson MedTech, executive director for Johnson & Johnson Center of Device Innovation at TMC, and director of the renowned Cohn Cardiovascular Research Lab at the Texas Heart Institute. Dr. Cohn has been deeply involved in developing the continuous flow total implantable artificial heart. In 2011, Dr. Cohn, together with Dr. Fraser, successfully implanted the first pulseless total heart replacement device in a human patient. The device has been developed at the Texas Heart Institute, and he'll be telling us more about it today. Dr. Cohn has published extensively, has more than 220 US patents or patents pending for medical devices, has been a foundational role for 9 venture-backed startups. So it's a real honor to have you today. We just learned also he's a musician in 2 successful bands and a magician as well. So it's a real honor to have you here today. Thank you so much.
Thanks for that great introduction, Leandro. And hi, everyone. I'm going to talk a little bit about what I think the total artificial heart is headed toward. I'm going to describe the history. A lot of it happened in Houston, so this is a very Houston-centric story. I'm going to talk about our efforts over the last year, 2 or 3, and then where I think it's going. Thank you very much for this opportunity. And my wife got me a T-shirt that says, "Help, I'm talking, and I can't shut up." I love talking about this topic to anyone that will listen. Um, Here are my disclosures. I'm the Chief Medical Officer, of course, you just heard. I have shares in, I'm a board observer. I'm severely conflicted, but I'll try to maintain equipoise. I think everybody listening to this talk knows that heart failure is a big, big deal. We spend a fortune on trying to take care of these patients, and it's not just the patient that suffers, it's their whole family. So why don't we just transplant them all? I think you know the answer to that. The busiest transplant year we had was 2 years ago. We did 4,169 in the United States, but that's still just woefully short for the 130,000 patients that are destined to die from heart failure in the United States each year. It's like 1 in 30. So, well, why don't we just make an artificial heart? It's not a new question. For the last 70 years, people have really tried aggressively to do this. My old boss, uh, Michael DeBakey, worked with a Argentinian surgeon, Domingo Leota, and came up with that device that you see in the middle. He recruited my last boss, Denton Cooley, to come down from Johns Hopkins and join him as a partner. Denton Cooley and Michael DeBakey combined did more heart surgery than was done in all of Europe back in the 80s and 90s. But Domingo Leota was frustrated that it was taking so long to try a human. Dr. DeBakey had done 7 calf implants. He was very busy, so he didn't have a lot of time to go to the lab. But 7 calf implants, the longest one went 12 hours. He talked to Denton Cooley and said, "Could you help me accelerate this?" Denton Cooley had moved across the street into St. Luke's as an overflow and founded the Texas Heart Institute in 1962. He said, "Well, why don't you bring a system over there and I'll look at it?" And by cover of night, Domingo Leota brought a second system over. And Dr. Cooley never put it in an animal, just looked at it and could immediately understand its, the nuances of it. And then in a very bold move, while Dr. DeBakey was in Washington, D.C., getting additional funding for the device, Denton Cooley sewed it into a gravely ill patient, Haskell Karp. A very, very brave man. He'd done a large ventricular resection and a Dacron reconstruction of Cooley endoaneurysmorphy. His heart was too weak to come off bypass. He had talked to the family preoperatively that if that were the case, he would put the artificial heart in. He was supported on the device for 64 hours. He had progressive hemolysis. Dr. Cooley had taken the original valves out and put the Jerry Wada valves in, which is like a folding taco shell. The hemolysis made it so they couldn't wait for him to get well. They had to hurry up and do a transplant. This is before cyclosporin. Tragically, he died 32 hours later of sepsis in April 1969. So this was the first human being to have an artificial heart done, implanted. It was done here at the Texas Heart Institute in Houston, Texas. And Michael DeBakey came back and was very congratulatory of Denton Cooley's efforts. No, not really. They had a big falling out over that. He fired Dr. Cooley. He fired everyone in the lab. They all went over to the Texas Heart Institute, which had already been established. And that was really the beginning of the Texas Heart Institute because all the people from the lab and every surgeon in the group had to decide, are they going to stay with DeBakey or go with Cooley? And it was just a real mess for a while. And for the next 40 years, the two of them really didn't speak. And as I mentioned, their competition fueled the growth of the Texas Medical Center throughout the 80s. The two of them did more heart surgery than was done in all of Europe, which is impressive. That original heart implanted in Haskell Karp, the gravely ill 46-year-old, is enshrined in the Smithsonian Institute. You can go see it. But its legacy lives on. It's been invented and reinvented and reinvented, the exact same mechanism, but with better materials, better manufacturing. And now it exists as a commercial product, the Syncardia, and all of the iterations work the same way. They had compressed air that went back and forth through tubes, inflating flexible bladders that would drive blood out of two rigid containers. Each rigid container had an inlet and an outlet valve. They're tall Hall, Medtronic Hall valves, specially designed Hall valves. And so it's a great way to pump blood. It's copying Mother Nature, biomimicry. But biomimicry is not always the best solution. That's why no one ever made a decent airplane with flapping wings. So this would support the circulation, uh, but it had challenges. As I mentioned, it became the Jarvik 7. You may remember that, Barney Clark in the 1982. The Symbion, Jack Copeland, the Cardio West. It's now called the Syncardia Total Artificial Heart. It's a temporary device. Why is it a temporary device? You've got two air hoses going through your body, which is kind of a liability. You have this box outside your body, which has to routinely be replaced every 3 months. It has pistons that go up and down. It actually has a dual backup system. When it switches to the backup, you immediately replace it. And even if it's doing well at 3 months, they replace it because they know they wear out. But here's the real challenge. The device, which sits in the chest, as brilliant as it is, will wear out at some point. It has flexible membranes that are going back and forth, four mechanical valves that are opening and closing with really high DPDT because of the mechanism of ejection. And so if it's doing 100 beats a minute, that's 1 million beats every week. It's 52 million beats a year. No man-made device can last indefinitely like that. Still, they have 70% 1 year survival, which is incredible because all these patients are facing imminent death. So the device really, really works, but durability has been a challenge. So it's only used to support patients until they get a transplant. Um, there have been some long-term. We had one that went 4 years on the Syncardia. There's talk of a patient out there that's at 7 years. The stroke rate is very high, and I think it's just because of the mechanism, the way the thing works. Um, Infection rate's high, though Francisco Arabia, who's done more of them than anybody, doesn't have that problem. So it's a great temporary artificial heart, but the results are not great. And the idea is we need something better. Abiomed of Impella fame spent $250 million trying to develop an artificial heart in the late 90s. Bud Frazier was extremely involved. Instead of an external compressor, it used a little internal turbine mechanism that shuttled silicon oil back and forth, but still 1 million cycles a week. Bud in our Texas Heart Animal Lab did 150 of the 300 implants. And then 14 patients were implanted in 2001, 2002. Bud did 5 of them. He did the last one right before I came back down from Boston and joined him. Of all 14 of those patients, only 4 of them lived longer than 9 months. Rob Dowling had the longest survivor that went 17 months. And those four patients that went longer than 9 months all died when their devices failed. In fact, the patient at 17 months, it was a progressive slow failure. They asked him if they could change out his heart. He said, no, I'd rather die. Lots of challenges. So it was a big device. It used of power. It was the second successful device that used transcutaneous energy transfer. The Lionheart was the first, putting 38 watts through the skin, and showed us that transcutaneous energy transfer is a good option. Why have the LVAD companies not embraced it? That's a great question. I don't know. It was challenging to maintain balance between the systemic and pulmonary circulation, but its limited durability was the biggest challenge. So in 2004, after spending $250 million, they canceled the project. Now, many of you may know about this device, the CarMat. This is ongoing. This is Alain Carpentier's brilliant device. They started in 2010. Michael Mack, who I'm sure a lot of you know, is on the board of directors, and he shared data with me recently. It is kind of a complex device. It's sort of large. It won't fit in most women and in smaller men. But they've now done this, and this is 3-week old data. They've probably done 100 patients now. In the first 40, they had 13 mechanical failures that all resulted in death. We tried to start a U.S. early feasibility study. 3 patients were done. 2 of them died, both from Mark Slaughter at University of Louisville. Both died after 3.5 months when their device suddenly stopped. The patient at Duke was transplanted after 4.5 months, so one successful one. But based on that data, the FDA said stop, come back when you've resolved the mechanical failures. They're largely resolved, although we just talked to a European surgeon who's had 2 that capriciously stopped in a row, and both patients died. So it's a brilliant device. Is it brilliant enough? Remains to be seen. Long-term durability, completely unknown. So right now, from what I presented, it doesn't sound like the future of the permanent total artificial heart is very rosy. And that's what a lot of people thought as this story evolved and they shifted their focus to LVADs. And we all have lots of history with LVADs. I know you guys do tons of LVADs, Montefiore. And you may remember the XVE. We did the first 25 of those at Texas Heart. I say we, I was still in high school probably at that time. Bud Frazier did, but it was a big device, and again, was fraught with durability problems. Doing this, even 60 times a minute, it would last a year and a half. But you could take patients that were gravely ill, that were going to die any day, put that in. If they survived the operation, because it was a big operation, these were sick patients, color would return to their cheeks. Many of them got up and walked around. You could discharge patients home. But if you didn't find a transplant for them in a year and a half, the device would fail and they would die. And that's what our good friend Rich Wampler, many of you know him as well, Captain Hemo, I call him, was thinking when he was on a missionary trip in Egypt and watched 2 Egyptian workers use a shot off, basically a big Archimedes screw, to pull water up a riverbank to do irrigation. And he brilliantly reasoned, well, if it can move water against gravity, maybe you can use it to move blood against pressure. And he came up with this crazy device, which of course is a predecessor of the Impella. It was a long catheter going to a catheter pump, and it had an Archimedes screw right here at the back, and it had to spin really fast, 45,000 RPM. This is 1980. There were no motors small enough or powerful enough to spin this as fast as it needed to spin. There are now, Impella, of course. So they put the motor outside the body. It had a spinning cable threaded through a tube. He took this and showed it to Bud Frazier. Bud Frazier said, that's the craziest thing I've ever seen. Let's try it. He said, why isn't it going to break up the blood like putting fruit in a wearing blender? And Rich said, well, it's like running your hand through the flame of a candle. You see, your hand just sees the candle for a second and then has all this distance here to cool off. And the second time it may miss the candle. And so it's just briefly exposed to the impeller. They did cow after cow and showed that it didn't eat red cells. And after about 40 cows, they boldly put it in a gravely ill patient in 1988. This patient had had a heart transplant 6 months earlier. He came in an acute humoral rejection. he would have died. His lips were blue, his lungs were filled with fluid, he was anuric. In a 45-minute operation, they sewed a graft to his iliac artery. They thread this up right across the aortic valve. They turned it on. Within a minute or two, his lips went from blue to pink. He started urinating gallons of urine. His chest x-ray cleared over the next 12 hours. Um, Unfortunately, his cable snapped after 2 days, but at that point, they'd started him on OKT3, which was a new drug at the time. It reverses humoral rejection. His heart started beating. He was discharged from the hospital 10 days later and lived another decade. So that's the first human being to have a rapidly spinning thing inside the body. They had a big press conference. It was great. And one of the people in the back asked Dr. Frazier, well, Dr. Frazier, uh, how come it doesn't break up the blood? And he said, well, that's an excellent question. You see, even though the rotor is turning 2,700 times a minute, it's like passing your hand through the flame of a candle. And everybody was very congratulatory. After the press conference, Rich Wampler came up and said, Dr. Frazier, great job. He goes, oh, a bit of a shoestring catch, Rich. And he goes, one correction, you said the device turns 2,700 times a minute. And Bud said, yeah. And he goes, it's actually 27,000 times a minute. And Bud famously said, that's a good thing I didn't know that. I never would have tried it. Anyway, fortune favors the brave. Um, that gave birth to all the rapidly spinning pumps, the Micromed, the Jarvik, and famously the HeartMate 2, the most widely used continuous flow pump of that period. And I think you guys know about these pumps, and that they're the first successful human one was done at the Texas Heart Institute in a 17-year-old boy, Everardo Flores, on November 2003. I just come down from Boston. I didn't have my ticket yet, so I watched from the head of the table while Igor Gregoric and Bud put this in. It was so much smaller than the old devices. It was easier to implant, so fewer patients died from the magnitude of the operation. It's quieter, use less energy, but most importantly, it didn't wear out. In fact, Walt Dembitsky has a patient that's 22 years out now this year. And Bob Cormus told us that there are 500 patients that have had one for 15 years or more. And Dan, you probably have some patients that are out that far.
Not
Anyway.
that long.
Well, you're young still. Anyway, so this was the beginning of the continuous flow pump craze, and it gave birth to tons of pumps. And I show this slide because just about all these pumps are dead now and gone, but we have new ones. So the Heartware, the MVAD, the Micromed, which became the Reliant, the Jarvik, it's the Circulite, but now there's 20 more, and the Core Wave and the Brio and the Core Heart 6, and there's tons of great pumps. So Bud Frazier said, I had just come down. I was looking for something to do. He said, Billy, why don't we leverage these little pumps to rethink the artificial heart? Since at that point, there was just a syncardia. So Rob Jarvik gave us two Jarvik turbines. These things were $75,000, $80,000 each, but he was our good friend. We did all of his training courses at Texas Heart. Bud and I cut out the heart of a cow and put these two turbines each in the left and right atrium with a lot of felt, and sewed the two end grafts, aorta to pulmonary artery, the left pump to the aorta end to end, the right pump to the pulmonary artery, and then flow probes. And I thought it was scheduled for a chronic. I didn't know if we were going to get that far, but I said, well, let's close them up and take them over to the ICU and see what happens. There's a lot of argument back and forth about that, but ultimately we did it. And then I went upstairs to check my email. It was hemodynamically stable. And they said, hey, you better come back down here. And the animal, here's this angiogram. The animal was standing in a stanchion eating hay. And I said, no way. And so he had no pulsatility. He had a cardiac output of about 9 liters a minute. That's a max that you can get out of a Jarvik, 8 or 9. And he went 21 days before one day he stood up abruptly and knocked off one of the controllers and his right pump stopped. We got it hooked back up in a couple minutes, but that was enough that he whited out his lungs and died shortly after. We were really excited about this. We did it 2 or 3 more times with those same Jarvik pumps, but they started getting pretty nasty. And Rob Jarvik was not an unlimited resource as far as giving us those pumps, but Micromed was. It was there in Houston. It was a company Dr. DeBakey started. Bob Benkowski, who some of you may know, was the lead engineer and a good friend of Texas Heart, and a good friend of Denton Cooley's, and he gave us a ending supply of these pumps. But the way the pump was configured, you couldn't put it in the atria. There was, and the inlet cannula it had wasn't suitable for that. It wouldn't fit right. So I went and got some Dacron polyester from the fabric store, same place Dr. DeBakey went when he was working on the aortic graft. And I took a styrofoam cone and sewed these little stockings. And then I went to medical device prototyping headquarters. I go to Home Depot all the time. It's my favorite place when I'm working on something. And got drywall tape. That's the stuff you put on between the panels of drywall so that you don't have seams and you can paint your walls nicely. And then bath and tile caulk, room temperature vulcanizing silicone, and made these little constructs. Built them up like a pinata with multiple layers of drywall tape and silicone. And so they were soft enough that they could conform to the necessary geometry. You could cut them and they wouldn't fray. The needle holes didn't bleed because you were going through silicone and a mesh. And on the inside was a beautiful sheet of Dacron polyester, the material that Dr. DeBakey taught us all you could put in the bloodstream. And with this, we cut out the heart on cardiopulmonary bypass in the cow, sewed one of these to the right atrial remnant and put on a turbine, so the other one to the left atrial remnant, second turbine, cross the turbines and hook their outlets to the aorta and the pulmonary artery. And there's that animal 7 weeks later walking on a treadmill. There's the late, great, legendary Denton Cooley. He would come down a lot to watch what we were doing and was very congratulatory and supportive. I'm holding the molasses there. There's Bud. So we did this over and over and over again. Look how much smaller our device was than the AviaCore. The AviaCore had 160 moving parts. We had two. Here's a dual HeartMate 3. This is long before the HeartMate 3 was approved for clinical use, but we did the GLP studies, and so Kevin Bork let us have a couple on 3 or 4 occasions. And here's a summary of the 68 times we did this. A lot of work, a lot of work. Most of them were micromeds because they were there in Houston, but you can see the breakdown. We cut out the whole heart. We put in pressure lines so we can see left and right atrial pressure and PA pressure. Only 30 of them went more than a week. 8 of them did well enough that they could be exercised on a treadmill, and only 3 of them did 90 days. But we were getting better and better, and we realized that animals were probably harder than patients. And for a lot of reasons, we now know that's completely true. We had some challenges with balancing the two. There was some automaticity because these continuous flow pumps, as the inflow increases, the flow through them increases. But we were always messing with the 2 controllers, and we required 2 controllers. Bob Minkowski was trying to come up with a way to run them off a single one and make a dual controller. And then right pump thrombus was our nemesis. A third of the animals died when a deep venous thrombus would go into the right pump and take it out. Here's actually, these are modified Reliant pumps, Micromed pumps. You can see clot on the right, but it was small. It didn't use a lot of power. We thought durability would be great. So Bud said, "Hey, Billy, I think we ought to think about putting this in a patient." I said, "I'll follow your lead if you think that's something we can get away with." Well, we didn't have to wait too long to find a patient, but we knew that if we sewed drywall tape and bath and towel caulk into a patient, we would both lose our licenses and go to jail. So I found stuff in the sterile supply that we could replace these with. Instead of drywall tape, which was $6.99 for a 25-foot strip, we used hernia mesh, $1,000 a sheet. Instead of Dacron from the fabric store, Bard cardiovascular patches, and then NuSil medical silicone that they use to put over the screws when they put in a pacemaker so you wouldn't get in leaching. And with that, made the world's first sort of approved for implantation continuous flow artificial heart. HeartMate 2 got approved in 2010, halfway through. So they were approved, and the FDA approved stuff. They don't practice medicine. They don't tell you how to use it. You can use it off label, but it was approved for implant. The hernia mesh, silicone, cardiovascular patches were all approved. everything in this picture except that black band tie. We did two animals with that exact configuration, showed it fit great. It was small, it worked fine, and then waited for a perfect patient. We didn't have to wait long. This is a 52-year-old beautiful man, Craig Lewis, very supportive family. He had cardiac amyloid. He also had hepatic amyloid and renal amyloid. He was on dialysis. He was in late stage liver failure. He was in and out of consciousness, but we got him to consent. He was an engineer. He thought it sounded like a great thing to try and thought if he could contribute because he was on a tandem. He wasn't on ECMO. He was on a tandem, but kept arresting on the tandem, and we had nothing left to offer him. We thought if we put this in, maybe he would do well enough. We could go do a bone marrow transplant on him at MD Anderson and then consider doing a multi-organ transplant. It was hubris, but it would allow us to accomplish several goals, and maybe he'd have a chance. Here he is coming out of the OR. Here he is 2 days later, off the ventilator. It was trached. You can see how yellow he is. He was working on his computer and drawing us pictures of control systems to allow the two pumps to talk together. He's a brilliant, brilliant guy. Tragically, his liver enzymes continued to rise, and he got so he couldn't stay awake. And the family said, "What do we do now?" We didn't really have a good response. And after some very difficult discussions, they asked that we turn the device off. But his hemodynamics were great throughout the 5.5 weeks, and he had great perfusion, and we got some great publications out of it. Bud and I did a TED talk about it. But the most important thing that came out of that, and we got a lot of lay press. And when I was young, I used to read Popular Science. It was my favorite. It was the only subscription I've ever had. And I would mark on the calendar when Popular Science was going to come. It was a red letter day for me. And I would read every advertisement, every article. I was just a total science nerd. So being on the cover of Popular Science, I said, okay, I'm done. I'll go home, wait for a happy death. I just, I thought that was really cool. But the most important thing that came out of it is we met this young man. He was young then. He's less young now. This was in 2011. This is Daniel Timms, who came up with the idea for the bivacor heart that I'm going to show you in a second, while his father was dying of heart failure during his PhD studies at QUT at Prince Charles in Brisbane, Australia. And he gave a talk on this in Paris at a meeting that Bud Frazier was at. And I think all of you have seen Bud Frazier when he goes to the microphone. It's never a happy moment for the speaker. Because he says, describes all the things that they didn't know that have happened before and stuff. He can be pretty acerbic, and he means well. And so Daniel described he hadn't actually made the device or done an animal implant, but he had an impeller that was double-sided. The motor was outside a box spinning it, and he could translate the rotor inside these volutes, and showed that as the left got closer and closer, the left pump became stronger than the right. As it moved further away from its face, the left became weaker than the right, and offered that as a potential way to balance left and right circulation. And Bud goes to the microphone, and everybody's going, "Oh, this poor kid." It was hubris for an engineer to present at a heart surgery meeting anyway. And Bud said, "Well, I don't know what the future of our field is, but it's going to be something like this young man just showed." And instantly, Daniel was a celebrity. I wasn't at the meeting, but they said, "You got to come to Houston and meet Billy." It was on my calendar. He flies in on his own dime, dumps a bunch of crap out of his backpack that looked like an alternator from a car and a bunch of wires hanging out of it. And about 6 hours into our 30-minute meeting, I'm saying, "Look, you're not leaving Houston. You're coming here and you're bringing your team." And he said, "Well, we don't have any money." I said, "How much money do you need?" He said, $2.5 million. I knocked on exactly one door. This is Jim McInville, furniture maker in Houston, who's very philanthropic, who Bud and I both knew really well. Within a week, I had the $2.5 million in hand. Daniel brought the whole team in. Some of these people are are fundamental to Vivacor's success, specifically Frank Nestor, Matthias Kleinheyer, Nick Graytrex, Toru, Nobu, and there's Daniel. And so these guys have I work with them now extensively, And this team has stayed together and has been incredibly impactful. This is the device that we now have. It's the derivative of that effort. It's small, much smaller than a syncardia. It has one moving part that's floating in an electromagnetic field. The left-sided rotor, that flat thing, takes the left atrial blood and pumps it out the aorta. Those tall fingers are the right impeller that take the venous blood and pump it to the lungs. There's about a liter a minute shunt over the outside of this from the aortic pressure to the pulmonary artery pressure. This is the brushless DC motor that makes it spin. These three electromagnets are adjusting about 2,000 times a second based on sensor data from these sensors, which is acquired 20,000 times a second. And that's what keeps the impeller floating and determines how far to the left or right it needs to be. It looks at how much power it's drawing and takes it to the zero power point. That was what Daniel Tim's PhD thesis was this virtual zero power balancing. They do it in maglev trains. He came up with the idea of using it in an artificial heart. It's not unlike the HeartMate 3. HeartMate 3 uses a virtual zero power thing too, but they don't try to translate their impeller to try to optimize balance between the left and the right. And that was just the brilliance of this. We're very fortunate to live in the current era because this whole pump exists as a digital file, meaning it was a design file on a computer, which meant we could use 3D printing to iterate on a daily basis. And we did. We would print tons of left-sided rotors, tons of right-sided rotors with subtle differences, and left-sided volutes, that's the chamber in which the left rotor spins, and right-sided volutes. So here, for example, all these in the front are left-sided rotors. All these in the back with the little tongs sticking up are right-sided. And so, let's see here. Yeah, these are all right-sided, these things that look like Stonehenge. And it turns out, and then, oops, sorry, right-sided and left-sided impellers. And then we, tons of different volutes. So then we created a machine that would spin every rotor in every volute at every speed against every resistance and plotted all these performance curves. So this is just one left-sided impeller in one left-sided volute at lots of different pressure heads. We had a valve on it, but at lots of different spacing. We had a vernier that we could move it a quarter of a millimeter at a time to show how the efficiency changes, because this impeller needed to match with a right impeller that would perform the right flow at different RPMs. So here's a right impeller and a right volute. So it was wildly complex. It took thousands and thousands of machinations to determine what's our best left volute, what's our best right volute, what's our best left impeller, what's our best right impeller. And this allowed us to digitize it. And Matthias Kleinheimer, one of the engineers I showed you before, wrote code that went through all of it, and it determined that, hey, that's the best right side impeller, that's the best left side impeller. With that data, we made a 3D printed plastic heart. So here, through this really thin layer of plastic, and that was the challenge with plastic, is the layers had to be really thin. This is the brushless DC motor with 12 electromagnets that work with 10 really strong rare earth magnets right under here, neodymium iron boron. And then here are the 3 electromagnets that are going to work with 2 ring magnets on this surface to keep it levitated. And there are the 3 eddy current sensors. But that allowed us to do hemolytic testing to see that it didn't consume red cells and that it didn't have undue shear. And then in a perhaps hubris experiment, we sewed our printed plastic heart into a cow. So there's a cow who's not too concerned that his heart was 3D printed. We could only go a couple days with these, though. Those thin layers of plastic were hygroscopic. They'd soak up water and they'd warp, and it had to be absolutely flat to work. But this allowed us to tweak different geometric features and design features of the pump to really get our design figured out. And then we said, okay, time to start doing chronic implants. Well, we couldn't do them with plastic, but I point out here that the animal has no pulse. As we started to heart surgeons and cardiologists about this, there was a lot of pushback on no pulse. Well, these 68 animals that we'd done before all did fine without a pulse, or they did pretty fine, but there are some compelling reasons to make a pulse. The reasons we don't think you need one is if you take confocal microscopy and look at capillaries, red cells go through them in single file, and there is absolutely no pulse at the capillary level, and that's where all life takes place, right? Um, all of our animals had normal labs, suggesting their end organs, their kidney and liver and lungs, didn't care if we had a pulse. But we did see patients, and maybe you guys have seen this. If you have a tight carotid lesion or a tight popliteal lesion, and the rate of the LVAD spinning in a patient with a weak heart, they stop opening their aortic valve and they have diminished pulse. Some of them come into the ER with massive strokes or cold legs because they thrombose beyond a narrowed lesion. Having a pulse helps you wash out beyond a narrowed lesion. This whole GI bleeding signal that we see in LVADs, a third of them have GI bleeding. There's a lot of evidence to suggest that may be related to a consumption of von Willebrand factor and pulsatility. Endothelium that's doing this releases von Willebrand. And then pulsatility will certainly increase pump washout. Well, we can make a pulse. This is a digital pump. And because the impeller is so big, 900 change in RPM every second gives us a 40 millimeter delta between systolic and diastolic. You can feel a palpable pulse at the wrist. The pulse ox picks up a signal. And more importantly, you can get an accurate blood pressure with a blood pressure cuff. So the patient can go have a home blood pressure cuff or go to Walgreens and know what their blood pressure is. So for that reason, going forward, we decided we're always going to run it in pulsatile mode. The current device, you can't turn the pulse off. It's at least on, but you can go 300, 600, or 900. And every patient, once they're in the ICU, we put them on 900 pulse. So there's a pulsing plastic printed bivacor. You can see my thumb and fingers are being popped apart. And a lot of people say you can't have a pulse with a spinning pump. That's not the case. And you can see our flow goes up to 20 liters and down to 0 liters. Actually, a little less than 0 liters. That was with a 1200 RPM pulse. We now only do 900. But very compellingly, there's an animal walking on a treadmill with a chronic device, and I'll show you how we did that in a second. But how many of you would look at this arterial tracing and say, oh, that's a rapidly spinning continuous flow pump that's spinning fast and slow? But that's exactly what it is. Palpable pulse ox picks up, blood pressure cuff works. Well, when we wanted to do longer term animals, we couldn't do it with plastic printing. We weren't ready to machine it yet because we were still finding the perfect design. So we use selective laser sintering. It's a way of 3D printing with metal. You take metal dust. It looks like dust. If you look at it under a microscope, it's perfect 30 micron spheres, 1/30th of a millimeter spheres. And it spreads them out in a perfect flat sheet, and then a laser melts them together. And it puts down another sheet, and the laser melts those together. And it does that for 12 hours. It takes your computer design and turns it into a metal part. So there's the laser printing a bivacor, melting the fine dust together. After 12 hours, you have to put on respirators and hazmat suits because this dust, if it gets in your lungs, it's lethal. You brush away the dust, and there, rising like Venus from the mist, is the first titanium bivacor. We then electropolished it, and here we are putting it in our first cow. There's Rich Wampler, who came for the experiment. You can see here's the whole bivacor team. Steve Parnas, who assisted me a lot back in those days. There's Daniel Timms, Nick Graytrex, and Matthias Kleinheier, Toru and Nobu, for bivacor team to this day. And there it is. Here we are coming out of the OR. And I just show this. We couldn't do this kind of work if we didn't have this kind of team. Coming out of the OR, Kelly Harms always rides with the animal to make sure nothing gets yanked. That's Gil Costas, our veterinarian. There's Daniel Timms. There's Nick Graytrex. Bud Frazier built this team over years and years and years. And I was just privileged to work at the Texas Heart Institute with this incredible resource that allowed us to do this kind of work. Um, we did animal after animal after animal. We would exercise these animals on the treadmill. We got smarter with every animal and better at taking care of them. And other surgeons came down, Rob Dowling, Francisco Arabia, um, Dave McGiffin, uh, Carmelo Milano, and everybody brought more to the table. And of course, Alexis Shafi at Texas Heart, and we got better and better at implanting it. This is one of my favorite animals. This animal put on over 80 pounds of lean beef in the 3 months he had the Bivacor, and showed us how the cardiac output would go up just with exertion without touching any controls, just based on the afterload reduction and blood coming into the chest. So then after that, we froze our design. We did design for manufacturing because we couldn't 3D print it. It had to be milled out of titanium and laser welded. We figured all that, got that behind us, and then we started having talks with the FDA. We'd done 40 chronic animals at that point. Challenges with 30 days survival, mainly from infection. These animals lie in their own poop. We try to keep the cages clean. Their central lines were sewn in, so you'd have to keep that in place for 30 days. That was a frequent site of infection. But we had great interactions with the FDA. Our lead reviewer uh, could not have been more supportive, and the team was very supportive. They told us we didn't have to do GLP. It could be GLP light, meaning like a GLP, but we were allowed to be involved in the care. They said, we want 5 animals to go 30 days, 5 animals in a row to go 30 days. These are the 5 animals. We went back and forth about the histology, some things they were worried about. We went back and got older animals and showed them what they needed to see. And so, based on that, and also while we were doing this, we were doing our durability. We now have 8 pumps that have been pumping for almost 3 years, and 2 older previous generations that were our final generation that have been both pumping for almost 6 years, including that big cow, Typhoon Freeze. After we sacked him at 3 months, we washed off his pump. It's been pumping for 6 years now. We had to do biotox, short-term biotox for brain transplant. We have to do longer for BTT, but we're doing that now. Here's our hemolysis data. We know that our device at 12 liters a minute performs about like a HeartMate 3 at 5 liters a minute as far as hemolysis. So it's the best hemolysis we've ever seen in a spinning pump. And that's because the gaps, the HeartMate 3 was proud to say, and they should be, that they had the largest gaps of any LVAD. That means more than the HeartMate 2, more than the Jarvik, more than the Heartware, more than any pump. It was 500 microns. That's 1/2 of a millimeter. The gaps in our pump are 4 millimeters to 12 millimeters, depending on where you look. So our gaps are just 10 times bigger than any pump heretofore previously, and that manifests in much better hemolysis function and metrics. And we're now doing von Willebrand assays. It looks like we're next gen results there as well. This is what the device now looks like. The patient has to carry this big controller. It weighs 6 pounds compared to the Freedom, the Syncardia Freedom 13.5 pounds, but it's all solid state, no pistons. And we know from electrical devices, you can make them incredibly small. Anyone with an iPhone or an iWatch knows that. Those are all going to migrate to be inside the pump. There's a little console like the HeartMate 3 that you can hook up and review data and program parameters. We have 2 LiPo batteries on the outside. There's another one inside. Each one will give you a 4 hours function because we're pumping 10 liters a minute for 10 watts. Here's our ambition. This is the device we have now, but we're moving all these electronics so they'll be actually in the can, and then the outside controller will be the same size as a HeartMate 3 once we do that. Right now, all the computing is done in here. When we do that, we think we're going to be able to compete with LVADs. Why do we think that? I'll tell you in a second. But this is our ultimate ambition, is to make it driven by a TETS. And we just did our first experiment with in vivo power, which is a really cool TETS system that uses almost like an ear ring implanted in the skin. and then a puncture that allows you to hook a ring together so it can't become disconnected. So this is when we think we get to here, we think will be a more attractive alternative than a heart transplantation. So here's where we are now. In November 17th of 2023, the FDA said you can start your EFS. It takes a long time to initiate a site. We picked 9 sites. Here they are: Texas Heart, Banner, Christ, Cincinnati, and Duke, Cleveland Clinic, NYU Langone, Columbia Presbyterian, University of Chicago. But you had to train all the doctors. Well, first of all, we had to get through the clinical trial agreement. So the money, the insurance, all the lawyers get involved. That goes back and forth forever and ever. Then you have to show up, train the surgeons. They have to come down and do animals with me and human cadavers. And then the cardiologist, the intensivist, the perfusionist, the anesthesiologist, their task. It took us about 6 months to get these first 4 hospitals trained. The reason these were our first 4 is Texas Heart, because Bud and I were there, and Alexis Shafi. Banner, because that's where Francisco Arabia was. Christ in Cincinnati, because that's where Rob Dowling was. And Duke, because that's where Carmela was. We got all that done by June and started implanting in July. Here's the first 5 EFS that we got permission to do, just 5 as a starting point. And here they are, and you can see the dates. We could have implanted them faster than that. We decided we should only have 1 patient going in at a time. But look how short the durations were. This patient only had his pump for 8 days. This one only 10. This one only 27. This one only 15. This one only 5. The FDA said, well, why is that? Are these patients so sick that you're doing an emergency transplant to salvage them? And we said, no, it's because they get so well. These patients are all status 1, and all these patients were walking in the hall on room air by day 3 or 4. And you can see here, this patient at Duke was walking over a mile a day. And they said it was the healthiest patient they'd ever transplanted at day 10. You can see the cardiac outputs these patients are having. That's why they're doing so well. And LVAD, you say, well, he's just got left heart failure. You want to find out if he's got right heart failure too? Put an LVAD in and turn it up. You can make these right hearts are not normally these patients. So LVAD patients can get a cardiac output of about 6 or so with exertion. We're getting up to 14 and a half liters per minute of some of these patients. And now we have even higher numbers, and I'll show you those in a second. But these patients are walking here. This one was walking almost 2 miles every day. In fact, on day 12, and 4 of these patients had Impellas in place and were dying of progressive right heart failure and going into renal failure, kidney and hepatic congestion. 12 days later, this patient did a 420-meter 6-minute walk, which is unheard of. LVAD patients at 4 months, you do a 6-minute walk, and about 2/3 of them can do over 400 meters. The third that can't, that's associated with poor long-term outcomes. So a third of LVAD patients can't even do that at 4 months. He did it at 12 days because of the incredible output. And it's not just the output, it's the low venous pressure. Our CVP and LAP, we can run them at 0. You can't do that with a volume displacement pump. We generally run them single digits, usually 5 or 6. So transcapillary gradients are greater than we've ever seen in this field. It still gives me chills when I see an X-ray with the device in place, after 20 years of working to see this thing. And I really do believe this is the world's first permanent total artificial heart for a lot of reasons, building on the success of rapidly spinning LVADs, the HeartMate 3 mainly. The world needs a rapidly spinning artificial heart, and this is it. Look at this. The patient did the 12-minute walk. Here he is, 8 days from his deathbed, from his operation. You can barely keep up with the guy. He's 6'4", weighs 280 pounds. No LVAD patient has ever walked like that on post-op day 8, I don't think. When we take the pumps out at transplant, this is our 27-day patient. We put a boroscope in to see if there's any evidence of galling, meaning if the metal ever touched metal, if there's any clot or anything inside. Each pump has looked like it just came off the factory floor. That's why we think these pumps are going to go as long as you leave them. We think they'll pump a decade. So this is our latest update. The FDA just approved us to do 15 more cases and suggested that some of these EFS patients we can enroll into our pivotal trial. While we were waiting for that information, we went to Sydney, Australia. And some of you may have seen in the news on November 22nd, that patient came back and was discharged home with this pump. He was going to the grocery store. He was washing his car. He was walking around doing about 2 miles a day, just randomly tooling around. He came back on day 104 and was transplanted the following day. That was about a month ago. We were supposed to do an implant in Melbourne 2 days ago, but the patient refused to sign his consent. Actually, no, another one in Sydney 2 days ago, but the patient refused to sign his consent. But we just got back from Melbourne and have done site activation there and done the animals with Dave McGiffin and oh God, I'm forgetting his name. The brilliant surgeon there. And so now we just submitted to the FDA permission to send our patients home. These first 5 that we did in the US had to stay in the ICU by the protocol while they're waiting for a transplant. So if you're in an ICU with 5 ventricular support, it precludes discharge, your UNO status 1. We just put in our paperwork. We should find by May 1st that we can send these patients home. They'll now be UNO status 2, and then we'll get longer term durability. Here's our first patient from the Texas Heart, Batson Avery, and here's the board of directors of Bivacor. There's Daniel. It's just a super. This is Orlando Suero, just a great anesthesiologist who's been involved, and Thomas, who's been just great. We have a long way to go, but our first 5 went perfect. No complications, no deaths. They're all home with their family. We just got approved to do 15 more. The FDA doesn't want us to do it short and long like HeartMate 3. They want us to get BTT in the bag before we even start on destination. But we're going outside the US to Taiwan, Japan, and Australia, where we can get longer durations before they get transplanted because they don't have the organ allocation that we do in the United States. Hopefully, once we get UNO status 2 in the United States, down from UNO status 1, because they can go home, we'll get some longer term data here as well. So this is my last summary slide. You know, continuous flow pumps are so much better than volume displacement in LVADs. They're going to be better for artificial hearts too. Someone just had to figure out how to do it, and Daniel Timms did. You can make a great pulse. They're smaller, simpler, less mechanistic complexity, use so much less power, and durability is going to be a whole new field. So I'm pretty sure the Bivacor Total Artificial Heart will be the world's first permanent heart replacement device. And if it's not, it'll be because somebody copied what we're doing and did it slightly better. So I thank you for your attention. I'm going to show one last slide. I know we're almost up on the hour. Is that okay?
Yeah, perfect.
Yeah, so I was Michael DeBakey's last chief resident. Bud Frazier did all of his medical school and general surgery with DeBakey, but we both worked for Dr. Cooley. And so there was this sort of red ants, black ants thing. But we would go through the tunnels, the hospitals are connected by a tunnel, and show Dr. DeBakey what we were working on while we were doing the twin turbine hearts. He died in 2008, so he never got to see the Bivacor tragically. And we would show him, he'd say, well, you see, it's very satisfying seeing someone work on this. I thought of this years ago, the hallmark of a good idea. Everybody's had it. But we would invite him to come over to the Texas Heart to watch us implant one. And he'd always say, oh, I'll see if Henny can get. He had this associate Henny Banning, and he never came. But then one day, Bud went over to his house and talked to him and said, we really love it if you would come. And he said, no, tomorrow I'm going to come. And I didn't know about that. He didn't share that with me. So I'm down there getting the animal ready, and the phone rings, and it's George Noon, one of Dr. DeBakey's close associates, the one that operated on DeBakey when he had a dissection. He said, hey, Billy, it's Dr. Noon. Dr. DeBakey's heading over in the tunnel. And I go, oh, my God. So I call Bud, and he goes, oh, yeah, he's coming. Great. He calls Denton Cooley. We took this picture. These are 2 men that hadn't spoken in 40 years. But here's Mateus Loby, some of you may know. Here's me. Here's Bud Frazier getting in my way. Here's George Noon. Here's Michael DeBakey and Denton Cooley, Eddie Manning, sitting down, chatting it up like old pals, like they hadn't had this 40-year separation. DeBakey then invited Cooley into the DeBakey Society. Cooley invited DeBakey into the Cooley Society. When DeBakey found out he was going to get the Congressional Gold Medal, he invited Denton Cooley to go to Washington, D.C. with him. So not only does this device have the potential to cure a lot of the challenges with heart failure, but it can mend badly fractured relationships. And that's all I've got. Thank you very much for your attention.
Thank you so much. That's a wonderful lecture and really, really inspirational. I think for all of us that do research or like translational research, I mean, you've gone through animal research, patients, international trials. So really congratulations for your work, and hopefully for fellows it's also very motivational.
Thank
Dr.
you.
Goldstein, do you want to start with a question?
Bill, that was amazing. I mean, that was really magical. I had not heard this talk before, and the detail you shared was just really phenomenal. Question: what is the inclusion criteria for the trial as it is now? What kind of patients are
Now, if I gave you a piece of paper and said, write down inclusion and exclusion criteria, you probably would get it just right.
Yeah.
You got to be older than 18, younger than 70. You got to have biventricular failure, and we give all the criteria for what you need to satisfy that. Although one of those patients, the one we did at Christ Hospital, had hypertrophic cardiomyopathy, so he had HFpEF.
No.
But so, you know, have to failed inotropes, can't be a candidate for an LVAD currently because your TAPC is too low and you've got TR and your right ventricular stroke index and all the things that you would think.
Yeah.
Pretty
And
straightforward.
what's your size limit at this point?
So, you know, the ABIACOR, you had to be 16 at T10 for Syncardia. There you go. There you go. All right, man. We are 8 at T10. So we think we can put it in an 8-year-old boy, in any grown-up, any adult. Yeah, we're about the same size as the 50 cc Syncardia.
Anticoagulation, antithrombotic therapy?
Yeah, so right now we're doing aspirin and Coumadin. Bud says we won't need the Coumadin once the suture lines are covered with neointima. And we did some animals without Coumadin. In fact, those 5 cows that we presented to the FDA were not on Coumadin. The cows have 4 stomachs and it's hard to manage Coumadin. As I mentioned earlier, we've seen some clot on the atrial suture line. And I think that's more related to technique and maybe even the material that our cuffs are made out of. Our cuffs are made out of the same material as Syncardia. Maybe that was a bad plan. We're revisiting that and trying to figure that out and looking at novel ways to attach the pump to the atrial remnants. Right now, we're leaving the annuluses like Syncardia. We're cutting away all the muscle of the ventricle, leaving a millimeter or 2 rim, and then leaving all that epicardial fat there and sewing through and trying to make sure the cuff is ducked inside. And we're rethinking that. Alexis Shafi and Iki Adachi, pediatric cardiac surgeon, brilliant guy, they both say, no, do interrupted, it'll avert. But then it makes a little crevice, but we're trying to navigate all that. So right now, we're going to stay on Coumadin until we fix that, because we get to see, you know, we take them out of transplant and we look at them and go, oh, it's kind of good, but I don't want to see any thrombus. And so we got to figure out a way to do that. And we've got some things on benches that we're exploring now.
Can you share a little more about the 2029 sort of panacea? How are you going to get a 10 power pump, 10 watt power requirement pump to go to 2 or 3, which is what you need for TETs, right? Is that a mistake?
Yeah, so the ABIACOR was 38 watts and it used TETs. The Lionheart was 25 and it used TETs. So it's 10 watts for 10 liters. And when a patient sits down and chills, this power, the flow goes up and down with activity autonomously based on afterload and venous compliance changes. When you get up and walk, all your veins in your lower extremity clamp down, you auto transfuse, all the precapillary arterioles and your muscles dilate up. Our patient in Australia, when he was in bed or watching TV, his cardiac output was 4.5 liters. When he would get up and walk, it would go up to 15 liters, you know, autonomous without changing the speed. So when you're chilling at 4 liters, it's 4 watts all in, both sides combined. At 15 liters, it's 15 watts. We're about a watt per liter per minute for both sides combined.
What is your best guess as why we have not moved to test quicker? Is it liability? Is it cost? Is it heat? It just doesn't make any sense to any of us.
Liability and
Monopoly?
cost.
Monopoly.
Yeah, liability and cost. In
Yeah.
fact, when hardware was still a thing, Kevin Bork was aggressively working on TETs, and Medtronic was aggressively working on TETs. When Medtronic folded, they said, "Oh, we don't need to do it, thank God," because there is liability if your battery. The real liability is if your TETs falls off, to keep the pump from stopping, you need to have an internal battery.
Right.
Well, there's this thing called hysteresis that is that internal battery charges and discharges, charges and discharges. We all know this from our phones. The battery gets worse and worse. And so throughout this whole era, we only had batteries that could go through charge discharge cycles for about 2 years. Now we've got some that are approaching 4 or 5 years. So, and that technology will continue to improve. So if you need an implantable battery, every couple of years, you're going to have to go in and re-op and take that battery out and swap it out. That's not attractive. That's why we like this in vivo power. It's 2 locking rings that can't come off. One ring is covered with skin, is implanted, and then it's pierced like an earlobe, and the second ring goes through it. And what we're thinking about doing is having a real test system and have in vivo power be the backup. So the patient can really be completely untethered, and run on in vivo power when they're swimming.
Amazing. Truly amazing.
We'll figure it out.
Well, thank you very much. That was a wonderful lecture. We really enjoyed it, and we can feel the passion you have for what you do, and that's always so motivating for all of us. So thank you so much.
Yeah, that's what my dad taught me. He said, passion is a powerful elixir, Billy. When you learn to fake that, the world is your oyster. No, I'm just kidding. No, I'm truly passionate about it. So thank you for the opportunity, and hopefully I ignited a couple of people on the talk. I saw there were 32 people on. So anyway, thanks for the opportunity, Leandro.
Thank you
Great
very
seeing
much.
you.
Have a nice weekend.
Bill, you go to Boston?
Yeah, I'll be there. I'm only there for the first 2 days, and we're having a investigator meeting on Saturday, but I'm giving the keynote at this design of medical devices meeting in Minneapolis. So I'm going to just zoom into the thing. But do you want to come to the investigators meeting?
Yes, I'll find you.
All right. Great. See you.
Thank you.
Bye, y'all.